In this video, we're going to talk about exponential functions. Now, you may have learned about polynomial functions before, where we use sums of powers of some independent variable. Things like y equals x squared plus 3, or maybe a little more interesting, y equals negative 2x cubed plus x minus 1. These kind of things here have variables in the base of the power, x to some power, x to some power, x to the first power here. Well, what if we take the variable x and we put in the exponent, like y equals 2 to the x? Now the exponent's up here, a little more difficult to work with, and a really interesting function. We call this exponential functions. An exponential function is written like this: f of x equals a times b to the x. Now, we have some important parts here. We've got the a value, which has to be non-zero. If it's 0, then this whole thing is 0, and that doesn't mean much. Okay, the b value, which is the base, is going to be positive. It has to be positive, and it can't be 1, because if it's 1, we just have 1 to x power, which is always 1. So we got the initial value, once again, is a, and this b is called the base. So the first thing we need to do is to be able to recognize exponential functions. Now, y'all go ahead and pause the video and take a quick look here and decide for yourself which ones of these follow those rules, that definition that we just looked at. Well, here we have, we're looking for y equals a times b to the x, following those criteria that we had a few moments ago. And how about this guy? Well, this one is an exponential function because the a value is 1, which is non-zero. That's good. The b value is positive, and the b value is 2.5, and the x is in the exponent. So that's a good exponential function. How about this guy? Well, this one's actually not, because the b value is negative 3. And so this is not an exponential function. We've got an a value of 2 and a b value of negative 3. And the reason why this doesn't work is because if you take negative 3 to the first power, we got negative 3. Negative 3 to the second power, we've got positive 9. Negative 3 to the third power, we've got negative 27. And the negatives are going to bounce back and forth, and we just can't do that. Also, when you get into fractional exponents, you can't take square roots and even roots of a negative number. So that causes lots of problems. How about this guy? Well, this looks like no, but let's think about it a little more carefully. A is 0.5, that's great. And then we've got this 0.5, 2 to the negative x. Well, if we think a little carefully about that, let me rewrite that down here. We've got 0.5 h of x is 0.5 times 2 to the negative x. Well, that's like 0.5 times 1 over 2 to the x, which is, well, 1 is the same as maybe 1 to the x. Can we put that there? Because 1 to any power is 1. So, yeah, this is 1/2. We could pull this x out here. And so this is totally fine to have a fraction in here. That's great. This just has to be positive and something other than 1. So yes, it is. So our b value is actually 1/2, or 0.5. And so this is a yes. And one more. How about this? Is this an exponential function? Well, here we have the variable x in the base. And no, that's not an exponential function. That's a polynomial function. So this is no. It's a polynomial. All right? All right. So that's the idea. Now let's go ahead and use these a bit. Here's an interesting legend. We've got a peasant in India who supposedly invented the game of chess. This is how the legend goes. And so he invented the game of chess, and the ruler is so excited that he wanted to give him a reward. So he called the man in and he said, hey, I like your game so much that I'm going to give you a reward. And the man thought for a minute. He said, I got a reward. Nothing big, just a real simple thing. I want you to take my 8x8 chessboard and let's put 1 grain of rice on the first square. Then we're going to double that and put 2 grains of rice on the second, 4 on the third square, and continue doubling until we fill up the whole board. And so the king said, "Oh, that's great, no problem. That's all you want? We'll give you the reward." Well, let's think about that for a moment. Let's see if we can get an exponential function. So we've got our 8x8 chessboard. I'll just draw kind of part of it here. Okay. And so on and so forth. And we're going to put 1 grain of rice here. Then we're going to put 2 here. Then we're going to put 4 here. Then we're going to put 8 here. Well, it's doubling every time. So since it's doubling, the base is going to be 2. So we have each time, for each new square, we're going to double that. Okay. So we have our initial value, and that is 1. Okay. And then we are doubling every time. Okay. And so our growth rate is 2. But we got to be careful of one thing here, because this is actually square 1, square 2, square 3, so on and so forth. So we have square 1 gives us 1, square 2, let me back this up. Square 1 gives us 1, square 2 gives us 2, which this, by the way, is 2 to the 0. This is 2 to the first. Square 3 gives us 2 to the second. Square 4 gives us 2 to the third, so on and so forth. And we'd have to kind of go back here and square 0, which doesn't exist. But what would that give us? Well, if we look at the pattern here, we're going backwards. 8 divided by 2 is 4, divided by 2 is 2, divided by 2 is 1. Well, let's think of this. Square 1 would give us 2 to the the initial square here would give us 1/2. Okay? So let's think about our initial value actually as 1/2. All right, so our function becomes this. Y equals the initial value of 1/2, and we have 2 to the x. There's our function. All right? Our growth rate here, and initial value, which we never really have a 1/2 grain of rice, but that'll work for us. So the interesting question, how many grains do we have in the last square? Well, if we use our function, we have y equals 1/2 times 2 to the x. In the last square, it's 8x8 checkerboard, so we would have 1/2 times 2 to the 64th. Now, it doesn't seem very big, but once the king here started pulling out all his rice, he really quickly realized that we have a problem here. This ends up being 9.22 times 10 to the 18th grains of rice. That's on the last square. Okay? If a grain of rice here is 0.3 cubic centimeters, let's say, what's the volume of this rice? Well, let's take this number. If you use your calculator, you'll get a little more accurate value. 9.22 times 10 to the 18th. And if we divide this by, well, actually, let's multiply times 0.03. We get a volume of 2.767 times 10 to the 17th liters. So, cubic centimeters, sorry. So that's a lot. And so if we go a little bit further and realize, hey, the world right now only makes 700,000 liters per year approximately. So how much rice is going to be on the last square? Well, we're just going to divide that by 1,000 because 1,000 cubic centimeters is a liter, and we end up with 2.767 767 times 10 to the 14th. And that is a lot of rice. If we were to write that all out, we've got about 2767. 1, 2, 3, 7. All right. So that is in liters. And so obviously this is impossible to have that much rice, but it shows us how quickly exponential functions grow. For a little extra challenge, you might figure out how much would there be on the entire board, and it's quite a bit. So, amazing growth of exponential functions. One more example of exponential functions is a growing population. Let's say we've got a petri dish here, and let's say that we have some amoebas, and those amoebas are going to double in size every hour. So we've done some tests, and we find out that they double every hour, all right? And let's say we started with 3 amoebas. So if we double every hour, we've got 6, 12, 24, 48, and this is growing pretty fast, and 96. Okay, so how does the population grow in time? Well, if we have y equals, our initial population is 3, so this is going to be our a value. And then our growth rate is 2 to the x. So that's our function, our initial value here. And we have our growth factor here. All right, and if you test it out, it'll work, because this is just 3 times, let's see here. So we've got, this here is 3 times 2 to the 0, because 2 to the 0 is 1. This is 3 times 1, actually 3 times 2, which is 2 to the first. This is 3 times 4, and 4 is 2 squared. This is going to take that and multiply that by another 2. So on and so forth, or 3 to the third. All right? And so that's how our exponential function grows. Okay? A lot of times in real life we have shrinking things like radioactive isotopes. Here we've got some radioactive isotope promethium-128. And these radioactive elements have something called a half-life. The half-life is the amount of time it takes for that element to decrease by half or 2/2 of its original quantity. All right, so let's say we've got 64 micrograms of promethium-128. So we're going to start out with 64 micrograms, okay? And we're going to have, it has a half-life of 1 second. So this stuff is disappearing really quickly. And so after 1 second, it's got 32. Then it gets cut in half after the next second. Now it's only got 16 micrograms. It gets cut in half, gets cut in half, gets cut in half, so on and so forth. All right? So let's make an equation for this. Well, what's our initial value? Well, our initial value here is 64. So we're going to start off with 64. And so we've got 64, okay. And here we have 64 times a half. That gives us 32. And if we take that value, 64, which was got times a half, and we multiply it times a half again, so after we multiply it by half twice, we get 16. And if we multiply it by a half 3 times, we get 8. So on and so forth. So the number of halves keeps increasing here. Here we have 64 times a single a half, 64 times a half twice, 64 times a half 3 times. And so that's where we see we get the function 64 times a half to the x power if x is a time. All right? Or we might say the mass at time t is 64 times a half to the t power for time t. All right? So is this function increasing or decreasing? Well, if we were to graph this, we'd find out that it is decreasing. all right? And it's shrinking, of course. And so that's called exponential decay, all right? So we've seen exponential growth in the previous examples. This is exponential decay. A good question is, will it ever equal 0 as it goes from left to right? Actually, no, it won't, because every time we half it, it will always have something left. So this is decreasing, okay, and it will never reach 0. So, to wrap this up, we got exponential decay and growth. Okay, exponential function here is growth if the b value is, change here, we have a exponential growth if b is greater than 1. If it's in between 0 and 1, we got exponential decay. All right, so there you go. So we can recognize two types of exponential growth and decay. And now we'll take a look in our next video about how to solve exponential equations.